Number 26. What are the units for the rate constant of a second order reaction? Now, in case you forgot the, the rate constant unit, um, you don't have to worry so much, because as long as the rate equals, say, k times either a squared or a times b for both concentrations, you can just exploit the unit and kind of rearrange them. However, you need to know the rate is always, rate has a unit of mole per liter per second. In other words, we have the molarity over second. It shows how fast the concentration change over time. That equals to K is what we want to know, and we don't have to worry about number other than the unit. So treat the unit as if they are numbers. Now the concentration of A has a unit of mole per liter, but they are being squared. Therefore, you have mole squared per liter squared. Now let's multiply both sides by liter squared, okay, and divide both sides by mole squared. That way we have only K, the rate constant, on the right side. So this is cancelled, that's cancelled. Okay, you have mole squared on the bottom and you have mole on the top. Then that means on the bottom you have mole and liter squared over liter. So you have liter on the top and then you have second equal K. This is like saying that mole, liter per mole is like saying the reciprocal of molarity, and that's over second, but you can also write it as this without having fraction form. So the answer is B. Okay, number 27. So that was 26. 27. A sample containing a radioactive isotope produces 2000 counts per minute in a Geiger counter. After 120 hours, the sample produces 250 counts per minute. What's the half-life of the isotope? Half-life. Okay, let's start out with 2000 count. It's like saying the count are like a concentration, and we have the time, just like we had the second in number 26, we have that as minute. So this is indication of rate, and some time left, we somehow got 250 counts per minute. Okay, in between that, we want to know how many half-life happened first. Well, one easy way, instead of using any calculation, is simply divide it by half as we go on. The definition of half-life is that any concentration you start out with become half, and we would like to know how long it takes. If it's a first order, we expect that to be constant. If it's zeroth order or second order, it's going to be different. Either it's multiplied by 2 or it's divided by 2 as each half-life proceeds. So 2000 to 1000 counts per minute, and then 500, and then we're gonna end up to 50. That tells us we have 3 half-lives. So we have first half-life on our first above the first arrow, second half-life, and third half-life. And we know from the question that it took 120 hours to go from 2000 counts to 250 counts. So from here to here, it took 120 hours. Okay. Now, it's not saying the first half-life, second half-life, and third half-life. The question implies just half-life. And we know there are multiples of half-life. Therefore, this has to be first order. And it has to be that way. Okay? Otherwise, they should write down like 15, 20, 30, 45, or like 45, 30, 15. And because we don't have that, this is a first order. And the first order half-life does not depend on the concentration. Meaning we have a nice interval of 40 hours for the first half-life, second half-life takes 40 hours, and the third half-life takes another 40 hours. So the answer has to be C. (28) In the rate limiting approximation for a two-step reaction, the overall rate of the reaction is always equal to the rate of blank. Oh, my bad. Okay. Alright. So okay, much better. So I'm answering 28 now. Okay, let me reread that. It's always equal to the rate of blank step in the reaction mechanism. Well, if you know the definition of what determines the rate, it's the slowest, no matter what. And let me illustrate it in case you're wondering. I'm gonna draw the funnel. Okay, this is probably the best analogy for you to understand that the slowest step determines our rate. So imagine we have funnel, and I know it's not perfect, but you know, please understand this is a funnel. And then I'm gonna pour, okay, it's kind of exaggerated. I have a beaker here. Okay, imagine it's a big beaker, but right now I don't have much space. So I have a beaker full of water, and I'm trying to pour this, okay? And imagine, you know, I'm increasing this, or let's say I have a hose, okay? I have a hose. And say I'm increasing the water flow down our funnel, okay? And then I have, say I have a flask. It's the water and it's dripping, right? Okay. What you need to know is that even if I'm increasing the water pressure or the inflow rate, no matter what, the rate of this flowing down really depends on the diameter of the funnel. So you can kind of expect, even though this is like a fast, it keep increasing with the water level rising above the funnel, but you will see the constant rate water dripping down our flask, and this represents our slowest step. Okay? So the diameter of our funnel determines how fast the rate of our water drips. So that's why the slowest step determines the overall speed of the mechanism. So answer is D. Now number 29. Okay. Alright, much better. Which of the following examples demonstrate the homogeneous catalyst? When you see homo, this means same in the prefix. In other words, we have a catalyst in the same state as that it interacts with. If you look at A, we have a platinum that's solid. The metal interact or that speeds up the reaction. and we have a gas, and we have different state. Therefore, this is heterogeneous catalyst. So 1 is wrong, it's hetero. 2, we have a gas that catalyzes decomposition of ozone. It's a gas and you have another gas, it's in the same state, therefore we can say this is homo. Okay? And for the hydrogen peroxide, decomposition is characterized by bromide ion. So you see aqueous, that's good. So that's a homogeneous. Okay, so these are homogeneous catalysts. Always remember that the catalyst speeds up the reaction without raising up the temperature. So answer is 2 and 3, which is D. Okay, moving to number 30. The diagram above represents the energy profile for the reaction. A plus B goes to C and D. So let me write it for you. A plus B is on the reactant side. We have a C plus D on the product side. And reaction progress is like, you can think like a time if you want, although that's not really accurate definition. The energy in between it is delta E, and the hill that this reaction needs to overcome is the activation energy, and that's what they're asking here, activation energy. However, we have a reverse equation, so let me draw the appropriate energy profile. Okay. Again, we have a reaction progress. On the horizontal, and then we have kilojoule of energy. Okay. Now, because it's reverse, it's gonna look something like, something like that. Okay. Instead of delta E that you saw in the left side, okay, now our hill is much smaller. This is delta EA. Okay. And I see this line to be 60 kilojoule, and the very top is about 90-ish, or 85 or 90. Okay. It's still something we have to overcome. It has to be positive, so you can eliminate D here. And our delta E does not change. Just because we reverse the reaction doesn't mean delta E changes. Actually, they do, I'm sorry. The magnitude doesn't change, it's just that here you have plus, here you get negative. Okay. But then again, the magnitude does not change. Alright, so looking at that, the delta EA, the activation energy, is about 30 kilojoule, and the closest we see is A, 25 kilojoule. Alright.